The GoFundMe linked below goes directly towards supporting a father and his young son in Gaza, and any donation or share makes a meaningful difference. Thank you. Welcome to the series, Manifolds from a Problem-Solving Approach. In this series, we work through the geometry of smooth manifolds by solving concrete problems. First, we need to lay down some common terminology and develop the tools to solve our problems. Part 1, this video, asks the motivating question: why do we need manifolds at all? We will see concrete failures of classical calculus and introduce charts and atlases. Part 2 makes everything rigorous. We pin down locally Euclidean spaces, smooth atlases, and differentiable structures. We also work through the sphere and torus as key examples and introduce partitions of unity. Part 3 studies maps between manifolds, smoothness, diffeomorphisms, rank, immersions, embeddings, and submersions. We prove Sard's theorem and the rank theorem. Part 4 builds tangent structure, the tangent space at a point, the differential or push forward, the tangent bundle, vector fields, integral curves, flows, and the Lie bracket. By the end of Part 4, you will have the complete foundational vocabulary of differential geometry, defined rigorously, motivated geometrically, and ready for real applications. Part 1. Why manifolds? The problem of calculus beyond R to the n. Let us start with the central tension of this subject. On one side, what we already know how to do. We can differentiate functions on open subsets of R to the n, and we have the chain rule, the implicit function theorem, and the inverse function theorem at our disposal. On the other side, what nature keeps handing us: the unit sphere S2, the configuration space of a spinning top, the torus T2, the double pendulum, and SO3, all possible orientations of a rigid body. The problem: none of these spaces is an open subset of R to the n, yet physicists and mathematicians differentiate functions and vector fields on them every day. On what rigorous basis? Let us make the failure concrete. We attempt calculus on S2, the unit sphere in R3. S2 is the set of all points x, y, z in R3 satisfying x squared plus y squared plus z squared equals 1. Attempt 1, use the ambient R3, take the function f of x, y, z equals z on S2, extend it to all of R3 as capital F equals z, and differentiate capital F. This seems to work, but there is a serious objection. The derivative we compute depends on how we chose to extend f off the sphere. Different extensions give different normal direction gradients. The calculus is not intrinsic to S2. It depends on the ambient space we chose. Our goal: a framework where calculus on S2 is defined without any reference to an ambient space whatsoever. Here is a second, equally fundamental failure. Find a single global coordinate system. The natural candidate is spherical coordinates. The map takes theta, phi to the point sine theta cosine phi, sine theta sine phi, cosine theta, with theta in the open interval 0 to pi and phi in 0 to 2 pi. But this map misses the North Pole, the South Pole, and the entire half circle where phi equals 0. It is not a global coordinate system. In fact, no global chart exists at all. There is no homeomorphism from S2 to any open subset of R2. The sphere is topologically distinct from any planar region. The consequence: calculus on S2 requires overlapping local coordinate patches that together cover the entire sphere. No single patch suffices. Geographers solved exactly this problem centuries ago. A geographer faces the same problem. The Earth is round, but a flat paper map cannot represent it faithfully all at once. The solution is an atlas of overlapping maps. Each chart represents a local region. Wherever two maps overlap, a transition rule converts between their coordinate systems. Here is the mathematical dictionary. A local map becomes a chart. The atlas is our collection of charts. And the overlap rule becomes the transition map, phi alpha composed with phi beta inverse. Let us define the central object more carefully. A chart on a space M is a pair U, phi, where U is an open neighborhood, a local patch in M, and phi is a homeomorphism from U onto an open subset of R to the n. The map phi assigns coordinates to every point of U. Why a homeomorphism specifically? First, it is bijective. Every point in U gets a unique coordinate tuple. Second, it is continuous in both directions. So the local topology of M is faithfully captured in R to the n. But homeomorphism alone is not sufficient. It gives us continuous local coordinates, which is good for topology, but not for calculus. To differentiate, the coordinate changes between overlapping charts must be smooth. Here is the geometric picture of a chart. Think of it as locally flattening a curved surface. On the left, we have the curved manifold M with an open patch U highlighted in gold. The chart map phi carries U over to the right. On the right, the image phi of U sits as a flat rectangular region inside R to the n. Perfectly ordinary Euclidean space where we can apply all of classical analysis. The chart is a homeomorphism from U onto its image in R to the n, a bijective, bicontinuous identification between the curved patch and a flat open set. Here is the stereographic projection chart on S2. The blue horizontal plane is R2 and the sphere sits above it. We puncture the sphere at the north pole n, shown in red. The domain of our chart is U sub n, the sphere minus the north pole. The formula for phi sub n sends a point x, y, z to x over 1 minus z over r, y over 1 minus z over r, projecting it straight down onto the plane through the north pole. Watch the orange point P move toward the north pole. As P approaches n, the projected image phi sub n of P shoots off to infinity, confirming that n itself cannot be covered by this chart. Now P sweeps down through the equator and into the southern hemisphere. Here the North Pole chart still works, but near the South Pole we would switch to the second chart, phi sub s, which punctures S2 at the South Pole instead. Now suppose two charts overlap. This creates the central consistency problem. Suppose two charts, U alpha, phi alpha, and U beta, phi beta, overlap in a non-empty region. A function f from M to R then has two separate coordinate representations on that overlap, namely f composed with phi alpha inverse and f composed with phi beta inverse, two functions on open subsets of R to the n. These two representations are related by the transition map phi alpha composed with phi beta inverse, which carries the beta coordinate image of the overlap to the alpha coordinate image. Here is the key insight. For the smoothness of f to be a chart-independent property, meaning f composed with phi alpha inverse is smooth if and only if f composed with phi beta inverse is smooth, the transition map itself must be C infinity as a map between open subsets of R to the n. This single requirement is what makes global calculus well defined on M. Let us see the transition map picture. We have three regions. On the left, the beta coordinate image in R to the n. In the center, a schematic of the manifold M. On the right, the alpha coordinate image. The gold region in M is the overlap U alpha intersect U beta, the points covered by both charts simultaneously. The overlap maps to a red region in the left plane under phi beta and to a gold region in the right plane under phi alpha. The left arrow is phi beta inverse, reading the left plane back into M. The right arrow is phi alpha, projecting M into the right plane. The green curved arrow is the transition map, phi alpha composed with phi beta inverse, going directly from the left plane to the right plane, bypassing M entirely. This is an ordinary map between open subsets of R to the n. When this transition map is C infinity, infinitely differentiable, calculus on M becomes globally well defined. Why require C infinity rather than merely Ck for some finite k? One could require transition maps to be merely Ck for some finite integer k. The choice of C infinity is deliberate for two distinct reasons. The practical reason: C infinity avoids carrying an integer k through every theorem and definition. Every statement works cleanly without tracking a differentiability count. The mathematical reason: there exist Ck spaces that are homeomorphic but not Ck diffeomorphic to each other. More importantly, by Whitney's theorem, every C1 manifold admits a unique compatible C infinity structure. So nothing is lost by working in the smooth category from the start. Convention for this entire course: all manifolds are C infinity unless explicitly stated otherwise. Before the formal definition of a manifold, let us recall some prerequisite topology. A topological space is a set X together with a collection tau of open sets. Three axioms must hold. The empty set and X itself are open. Arbitrary unions of open sets are open, and finite intersections of open sets are open. From these axioms, all the standard notions follow. A set is closed if its complement is open. A neighborhood of a point P is any open set containing P. A function is continuous if preimages of open sets are open. And a homeomorphism is a bijective, bicontinuous map, a topological isomorphism. Two further separation and countability axioms are required for manifolds. A space X is Hausdorff, named after the German mathematician Hausdorff, if every pair of distinct points P and Q can be separated by disjoint open neighborhoods. A space is second countable if its topology has a countable base. a countable collection of open sets from which every open set can be built by taking unions. Why do we need both? The Hausdorff condition ensures limits of sequences are unique and that points can be separated by smooth functions, essential for analysis. Second, countability ensures that manifolds are paracompact and admit partitions of unity, the fundamental patching tool we will use throughout the course. Here is the geometric picture of Hausdorff separation. We have two distinct points, P on the left and Q on the right. The Hausdorff condition gives us disjoint open neighborhoods, U containing P in gold and V containing Q in red, that do not touch each other. The intersection of U and V is empty. This is the Hausdorff axiom. Points can always be topologically separated. Let us now catalog which spaces are and are not smooth manifolds. In the smooth manifold column, R to the n itself, the model space, any open subset of R to the n, the sphere Sn, the n-dimensional torus, a product of circles, and the rotation group SON. In the not a manifold column, the figure 8, whose self-intersection point has no Euclidean neighborhood, the cone, whose apex fails the local homeomorphism test, and the Cantor set, which is totally disconnected. The diagnostic test: a space fails to be a manifold precisely at those points where no neighborhood is homeomorphic to R to the n. Locate those points and you have found the singularities. How do we know dimension is even a well-defined concept for manifolds? The answer is the invariance of domain theorem. If an open subset of R to the m is homeomorphic to an open subset of R to the n, then m equals n. Dimension is a topological invariant. This guarantees that dimension is well defined for locally Euclidean spaces. If one chart maps a neighborhood to R to the n, then every chart at that point must map to R to the n with the very same n. The dimension of a connected locally Euclidean space M is the unique integer n such that every point has a neighborhood homeomorphic to an open subset of R to the n. We write dimension M equals n and call M an n. The geometric content of invariance of domain is simple to visualize. On the left is R1, the number line. On the right is R2, the plane. An open interval in R1 and an open rectangle in R2 are highlighted. These two cannot be homomorphic. Invariance of domain says so. Since m equals 1 does not equal n equals 2. No homeomorphism between them can exist. The conclusion: dimension is a well-defined topological invariant. Every manifold has a unique, unambiguous dimension. Why should a physicist care about any of this? Many mechanical systems have configuration spaces that are smooth manifolds. The manifold is not an abstraction. It is the actual arena in which the physics happens. Here is a table of systems, their configuration spaces, and their dimensions. A particle constrained to a wire moves on S1, the circle, a one-dimensional manifold. A particle on a sphere has configuration space S2. The orientations of a spinning top with a fixed base are parametrized by SO3, dimension 3. A double pendulum has configuration space T2, the torus, dimension 2. A free rigid body requires both position in R3 and orientation in S3, giving a six-dimensional manifold. And in general relativity, space-time itself is a four-dimensional Lorentzian manifold. Newton's equations, the Euler-Lagrange equations, and Hamilton's equations all live on these manifolds. Without manifold theory, they are coordinate-dependent and ill-defined at singular configurations. And from the pure mathematics side, manifolds appear at the heart of every major field, manifold. In topology, the classification of surfaces, the Poincare conjecture in dimension 3, and exotic smooth structures on R4. In analysis, partial differential equations on manifolds, the Laplace-Beltrami operator, the heat kernel, and the Atiyah-Singer index theorem. In algebra, Lie groups, named after the Norwegian mathematician Lie, are simultaneously smooth manifolds and groups, linking geometry to representation theory. And in geometry itself, Riemannian, symplectic, and complex manifolds all generalize Euclidean geometry to intrinsically curved spaces. Let us now articulate the fundamental strategy that underlies all of manifold theory. The strategy has three steps. Step 1. Work locally inside a single chart, where everything reduces to ordinary calculus on R to the n. Step 2. Prove that any result derived in one chart holds in every overlapping chart, using the C-infinity transition maps to transfer the argument. Step 3. Use partitions of unity to stitch together local results into a single global conclusion. These three steps rest on three pillars. Charts and atlases provide local structure, C-infinity compatibility makes calculus safe and chart independent, and partitions of unity are the patching tools. Every major theorem in this course, Sard's theorem, the implicit map theorem, the rank theorem, and the theory of flows, is an instance of this local to global strategy. Here is the atlas picture made visual. On the left is a schematic of the manifold M. The first chart U1, in gold, covers roughly the upper third of M and maps it to a flat coordinate grid in R to the N. The second chart U2, in red, covers the left portion, overlapping with U1. The third chart U3, in green, covers the bottom, overlapping with both previous charts. Together, the three patches cover all of M. The collection of all these charts forms an atlas. The defining property of an atlas is that the union of all chart domains covers M entirely. We close part 1 with the key philosophical shift. A differentiable manifold is not defined as a subset of some ambient Euclidean space. It is an abstract space equipped with a system of local coordinate patches, and nothing more. 3 consequences for calculus. Smoothness of a function f from M to R is determined entirely by its coordinate representations, f composed with phi inverse, which are ordinary smooth functions on R to the n. The tangent space T sub Pm will be defined intrinsically via derivations, not by embedding M in some larger space. Every theorem about M holds natively, no extensions, no ambient spaces required. A final note, by Whitney's embedding theorem, every smooth n manifold embeds smoothly in R to the 2n. So an ambient space always exists in principle, but we never need to invoke it to do calculus. The intrinsic framework suffices completely. Let us summarize everything from part 1. The central problem: many natural spaces, spheres, tori, Lie groups, are not open subsets of R to the n, yet support a full calculus. A rigorous framework is needed. The solution strategy: cover the space with overlapping local coordinate patches, require C-infinity transition maps between them, and do calculus locally in each patch. Prerequisites identified: topological spaces, the Hausdorff and second countable axioms, locally Euclidean spaces, and the invariance of domain theorem. Coming in part 2, the formal definition of a smooth manifold via locally Euclidean spaces, C-infinity atlases, and maximal atlases. Thank you so much for watching. If you found this helpful, like the video so others can find it, subscribe to stay updated as new problems drop, and comment with any questions or topic requests. See you in the next one.